Have you ever seriously wondered what it would be like to fall into a black hole? I'm not talking about the movie version. I mean what our best, most mind-bending physics says would actually happen. Well, today, we're going to do it. We're taking that journey, step by unbelievable step.
So, this is it. This is the ultimate cosmic question, isn't it? It's a one-way ticket to a place where all the rules of reality, everything we think we know, get pushed to the absolute limit. And maybe, just maybe, they even break. So, let's suit up before we take the final plunge. All right, before we get to the really wild stuff, we need to set the scene. We're approaching a part of the universe that is just fundamentally different from anything else out there. It's not just a place, it's a destiny.
Okay, so here's the key thing to remember. A black hole is born from the death of a truly gigantic star. When it collapses, its gravity becomes so powerful, so immense, that it actually warps the fabric of space-time into this incredibly deep pit that nothing can climb out of, not even light, the fastest thing there is.
Now, to really wrap our heads around what's about to happen, we're going to follow two stories. There's your story. You are the brave astronaut falling in. And then there's your friend's story, watching you from a safe distance. And trust me, your realities are about to split apart in the most profound way you can possibly imagine.
We've arrived. This is the point of no return, the event horizon. Now, this isn't some physical wall you'd bump into. Think of it more as a threshold. Once you cross it, your fate is completely sealed. And this is where Einstein's theories of relativity start to get seriously strange.
And right away, we see a total breakdown of any kind of shared reality. From your perspective, everything seems fine. Your watch is ticking away normally. You might not even feel anything special as you drift across that invisible line. But your friend sees something else entirely. To them, you start to slow down, your movements get super sluggish, until you seem to freeze right there on the edge, stuck for all of eternity. That's gravitational time dilation, and it is a wild ride.
And the visual effects are just as bizarre. You know, as you're falling, light from the outside universe can still fall in with you, so you can look back and see the stars. But if you try to signal your friend with a flashlight, well, they'd see that light get stretched out by the intense gravity. It would shift down towards the red end of the spectrum, getting redder and dimmer and redder, until you just fade away completely. Red shifted right out of existence from their point of view.
So, you just sail smoothly across the event horizon? No drama, right? Well, maybe not. This is where we have to hit pause on our journey, because modern physics has hit a huge wall, a paradox so deep it pits our two greatest theories against each other.
This whole paradox comes down to a really weird quantum rule. You see, right at the event horizon, particles are constantly popping into existence in pairs. One falls in, the other escapes. That escaping one is called Hawking radiation. Now, quantum mechanics says these two partner particles have to be linked, or entangled. But here's the problem. For other laws of physics to work, that escaping particle also has to be entangled with all the other Hawking radiation that already left. And here's the rule. A particle can't be fully entangled with two separate things at once. It's a fundamental contradiction. It just can't happen.
So we have this massive problem. You simply can't have it both ways. Something has to break. Do we throw out Einstein's beautiful idea that space should be smooth and empty at the horizon? Or do we throw out one of the absolute cornerstones of quantum mechanics? Physicists are, to put it mildly, deeply divided on this. And this leaves us with two main possibilities. First, there's the firewall theory. This idea suggests that to solve the paradox, the universe violently breaks that particle entanglement, creating a blistering, searing hot wall of energy right at the event horizon that would just incinerate you instantly. The other option is the no-drama theory, which says, nope, the crossing is smooth, just like Einstein said, and we're just missing some other piece of the puzzle that makes it all work out.
I mean, as the physicist Raphael Busso puts it here, the whole idea of a firewall just seems crazy to a lot of scientists. It completely violates this core idea of space-time being smooth and continuous. So this isn't just some small puzzle. It's one of the biggest fights happening in physics today.
So while the physicists debate that fiery paradox, let's assume you get lucky. Let's say there's no firewall and you've made it past the event horizon in one piece. Well, your journey is far from over. In fact, the most violent part is just about to begin, and it's all thanks to something called tidal forces.
It's actually the same basic physics that causes tides here on Earth, with the moon. But this is ramped up to an absolutely insane degree. The gravity of the black hole is pulling on the parts of your body closer to it, say your feet, way more powerfully than the parts that are just a little bit farther away, like your head. And the result of this difference in pull is, well, it's exactly what it sounds like. You would be stretched vertically and squeezed horizontally, pulled apart into a thin stream of individual atoms. Yep, just like a long piece of spaghetti. It is a pretty gruesome but totally unavoidable fate for anything that gets too close to the center.
So you've been spaghettified into a stream of atoms, and you're all heading for the very center. For decades, we thought this meant a one-way trip to something called a singularity, a single point of infinite density. But that picture, it's almost certainly wrong.
You see, the whole idea of a singularity comes straight from Einstein's math. But in the real world, infinity is basically just a sign that your theory has broken down. Infinity doesn't really exist in nature. So physics is telling us something else. Something even weirder must be happening at the core.
And there are some incredible new ideas being explored. One is the Planck star, where matter gets crushed down to the smallest possible size and then rebounds, maybe even in a huge explosion. Another is the gravistar, which would be a ball of dark energy that just looks like a black hole from the outside. And in a spinning black hole, the singularity might get stretched into a ring singularity, a kind of cosmic gateway that could, in theory, lead to a wormhole and maybe a whole other universe.
Honestly, each one of these ideas is weirder than the last, but they all point to the same incredible conclusion. The center of a black hole is where space and time as we know them just stop being fundamental. They dissolve. And that leaves us with the biggest question of all. If our reality can come apart like this, what is the deeper, more fundamental stuff that our universe is actually made of?